Okay, in this video we're going to talk about how to write down the equation of a plane in three-dimensional space. And that's what we're looking at here. This is a flat two-dimensional surface that extends infinitely in the two directions that it occupies in space, right? So here it is. This is a plane. And the way we're going to do this is we're going to think about, let's start with just picking a point on this plane. Okay, so there's a point. All right, now I'm going to give this point, let's think of its coordinates. Okay, I'm going to give it a name P, and we're actually going to view it as a vector. Any point can be associated with a vector in standard position, right? So let's view it as a vector. So its coordinates are x naught, y naught, z naught, say. Okay, and then what we're going to do is we're going to imagine a normal vector coming out of that point. What do I mean by normal vector? Well, normal means perpendicular. So that the normal vector is perpendicular to the plane. You see that? It is sticking out at a right angle. All right. So that normal vector is my vector n. All right. So that's going to be n. Now let's give that coordinates a, b, and c. Okay. So now what we want to do is we want to write down an equation for this plane. So what we want to do is we want to think of, for any point with coordinates x, y, z, what do those coordinates have to satisfy? What equation do they have to satisfy to be on here? Okay, so let's pick another point on the plane. Okay, right here. And that's a red point, so let's use red here. This is going to be the point x, y, z. Okay, that's the, let me decrease my exposure, maybe we can see that a little bit better. There we go. Okay, so that red point has coordinates x, y, z. And now what we're going to do is we're going to extend a vector. We're going to extend a vector from this first point, P, to the second point, x, y, z. All right? So let's have it draw that vector there. Okay? What would this vector be? Well, look, it joins the point x, y, z. It goes between this point, x, y, z, to this point, x naught, y naught, z naught. So to find this vector, we just take the difference. So that vector is going to be x minus x naught, y minus y naught, z minus z naught, right? That's the blue vector. Now, what do we know about that vector? Well, we know it lies in the plane, right? It is in that plane. And we know, therefore, that because the normal vector is orthogonal to the plane, the normal vector must be orthogonal, perpendicular to that vector. And what does that mean? Well, that means that their dot product must be 0, right? So if I take the normal vector and dot it with this thing, I have to get 0 as an answer. Okay, well, what is the normal vector? It's ABC. So let's run that through. What do we get? I'm running out of space here. Okay, just squoze it in. So that is the equation for a plane with normal vector A, B, C, and going through point x naught, y naught, z naught. So there we go. We've got the equation of a plane. Great. Now I want to show you one other way to write down the equation of a plane, and that's the way that I actually prefer. Okay, and what we're going to do is we're going to give this vector over here a name. All right, call this v. Okay, so the vector that runs from, that has this as its endpoint, v. Okay, so what did we do here? Well, this thing right here is just v minus p, right? So if I write that out again, what I have here is n dotted with v minus p. And I'm saying that that is 0. Well, let's expand this out. I know the properties of dot products is I can distribute. So I can write this as n dot v minus n dot p equals 0. And then rearranging terms here, I see that I have n dotted with v. Now what's v? V was the vector xyz equals n dotted with p. Okay. And this is the equation I prefer to remember for the plane. This is really nice because you see that it's saying that to find the equation of the plane, you just need to know the normal vector. You dot it with x, y, z. And then you need to know one other point on the plane, right? And so just set that equal to n dot that point. Right? So you can pick any point you want. And whatever this is, that will work here, and that will give you an equation of the plane. And I just like this. I think it's very neat and tidy, easy to write down, easy to remember. Okay, so let's look at this example. We want to find the equation, an equation of the plane through these 3 points. Right? So we know 3 points on the plane. Can we get the equation of the plane? Okay, well, let's take a look at what this situation is. So here are the 3 points. I've plotted them in space. Okay, so I think you can see there's probably a plane that goes through those 3 points. Now, how are we going to get it, though? All right. Well, what we need is a normal vector to the plane, right? Once we get that, we can write down the equation. So how are we going to get the normal vector? Well, we can create some vectors here that lie in the plane. For instance, if I label these points A, B, C, and I'm viewing them as vectors, all right, then I create a vector running from A to B, right? So let's go ahead and do that. Let's see what we get. Well, that's this vector over here. And I can create a vector running from A to C. So let's do that. That's this vector over here. Now I've got 2 vectors that are in the plane. Now how can I take those 2 vectors and create a vector orthogonal to the plane? Well, if a vector is orthogonal to the plane, it must be orthogonal to these 2 vectors. What produces a vector orthogonal to 2 vectors? The cross product. So what I'm going to do is I'm going to take the cross product of these 2 vectors. Okay? So what I did is I computed b minus a. That was this blue vector here. B minus A is the vector, if I just do that subtraction here, it's 2, 2, negative 3, right? And then this red vector is the vector C minus A. Okay, so how do I do that? Well, I just subtract component-wise, so I get 1, 5, negative 2. Okay? And we said we need to compute the cross product of these 2 vectors. All right? So we are going to cross these. Okay, well, let's do that. When I do the cross product, what I do is I cover up the first row here, and then I just take a determinant. I go this number times this number minus this times this. So negative 4 minus negative 15. Right, that's 11. Then I cover up the middle column, and I do it the other way. So 2 times negative 2 minus negative 3 times 1, and that is 1. And then I do the last column, and I do it the way I did the first one. Come on, stop rolling, pen. I go this way. 2 times 5 minus 2 times 1. So I do 8. I get 8. All right, so that's the cross product. That is our normal vector, right? That's what we were calling n before. So let's go ahead and plot that. That's sticking out right here. Okay, it's a big vector, so it's kind of coming off the screen here, but there it is, right? So remember what the equation of the plane was. It was n dotted with x, y, z equals n dotted with any point on the plane. Well, we have 3 points to pick from. Let's pick this one. It's got positive numbers and a 0 in it, so it's probably the easiest one to use. So I'll use C for P, right? So n is this, dotting that with x, y, z is this. What is n dotted with C? Well, it's 11 times 2 is 22, plus 1 times 3, that's 25. And there we have the equation of our plane. And we can go ahead and reveal that plane over here. That is the plane that we found.